Now let's look at what happens when we combine the gas laws we've looked at. When we combine Avogadro's law, Boyle's law, and Charles' law, we get a new equation known as the ideal gas law. And here it is written in a formula, PV equals nRT. We know capital P is pressure, capital V is volume, lowercase n is number of moles, R is the gas constant, which we'll go over in just a second, and T is temperature. So the four variables we've gone over in our other gas laws, but we haven't seen R yet. R is a gas constant, meaning its value is constant. Now, let's look at rearranging PV equals nRT. If we divide both sides of the equation by NT, we can see more clearly what R is. It's pressure times volume divided by number of moles times temperature. Let's look at the units. Number of moles will always have units of moles. Temperature in the gas laws will always be in units of Kelvin. Pressure and volume, however, do have different available units. Pressure can be PSI, it can be torr, it can be millimeters of mercury, it can be atmospheres. Volume can be milliliters, liters, meters cubed. So we are going to use a numerical value of R that is equal to 0.0821. This numerical value uses units of atmosphere for pressure and liter for volume. If we use different pressure units or we use different volume units, then our numerical value changes. So to keep things simple, we're always going to use this numerical value for R, and we will always, if necessary, convert our pressure to ATM and our volume to liters. Units are going to be very important, and we're going to have to take the time to make sure all of our units cancel out when we do an ideal gas law problem. Okay, so how are we actually going to use the ideal gas law to solve for anything? Well, let's take a look. Here is our equation, PV equals nRT. Now notice, unlike our other gas laws, we're not looking at an initial and final condition. We're looking at the pressure, volume, number of moles, and temperature for one particular sample of gas. So a typical problem would have you solve for one of the four variables. If you're solving for pressure, then you're going to use this formula. Pressure is nRT divided by volume. If you're solving for volume, you're going to use nRT divided by pressure. If you are solving for number of moles, it's going to be PV divided by RT. And if you're solving for temperature, it's going to be PV divided by NR, or RN. I meant to put it NR, but RN is the same. Now, typically, because R is a constant, we won't be solving for it. We will be solving for one of these four variable physical properties. So definitely have these four equations handy in your notes so you can refer to them. And let's go ahead and look at a typical problem. We want to calculate the number of moles of gas in a basketball, inflate it to a total pressure of 24.2 psi with a volume of 3.2 liters at 25 degrees Celsius. So I would encourage you to stop the voice lecture and see, based on the equations we just wrote down, if you can solve this problem. And when you're done, restart the voice lecture and we can go over it. Okay, so the first thing that I do is I write out what I am given. And when I do that, I see that the problem is asking me to solve for N. It gives me a volume, a pressure, and a temperature. Now, I know that my temperature has to be changed to Kelvin. So I'm going to add 273 to it, and I'm going to get 298 Kelvin. Now, my liters are okay, but my PSI is not, because I'm going to use the ideal gas law to solve for this. N equals PV over RT, and my pressure units must be in atmospheres. So in your textbook, you have a conversion between atmosphere and pounds per square inch. So we're going to go ahead and do that conversion factor right now, do that dimensional analysis. 24.2 psi, and there are, what was it, 14.7? Yeah, 14.7 psi for 1 ATM. Okay, and my calculator tells me 1.65 atmospheres. Let me just make sure our psi cancel out. So my pressure up here is 1.65 ATM. Okay, so I'm going to rewrite this. Okay, so here's all my data. I've rewritten it so I can easily see what my formula is. This is the formula I'm going to use since I'm solving for n, and I've written out all my terms here. My volume is 3.2 liters, my pressure, my temperature, and then my R value. So now I'm just going to plug in n is going to be equal to my pressure, 1.65 atmospheres, times my volume, 3.2 liters. And I'm going to divide that by R, 0.0821 atmosphere times liter divided by mole times K, and then multiplied by my temperature, which is 298 Kelvin. Now before I do my math, I'm going to make sure my units cancel out. Okay, so I have atmospheres here and atmospheres there. Atmospheres divided by atmospheres, 1. I have liters here, I have liters here. Liters divided by liter is 1. I have Kelvin here and I have Kelvin here. Kelvin divided by Kelvin is 1. The only unit I'm left with is moles, which is exactly what I'm solving for. So now I'm going to do my math here, multiply these two together, and then divide it by the product of these two multiplied by one another. And my calculator, where's my pen, tells me 0.0214 moles. I guess I should just have 2 sig figs, 0.021 moles, since this value up here only had 2 sig figs. So that's my final answer. And if you got that as your final answer, give yourself a big pat on the back. And I want to say, does this answer make sense? Yes, this is a reasonable answer. If I had gotten something to some negative power or 2,000 moles or something like that, that would not make sense. I have a relatively small volume, even though I have a high pressure, relatively small volume, normal temperature, so my number of moles aren't going to be that great. And just to give you kind of a way to figure out if your answer makes sense if you're looking at moles, at STP, let me just go to a new page. At STP, which is standard temperature and pressure, 0 degrees Celsius, 1 ATM, 1 mole of gas occupies 22.4 liters. So if you can remember this, you can use this as a conversion factor, but you can also use this as a gauge to figure out if volume or mole answers make sense if you're dealing with temperature and pressures that are near STP.